Hello everyone. In continuation with the Thinking Machine series, I would like to introduce another point of view for building thinking machines. You should look at my earlier video series to get better context and continuity, which will help you get into learning groove. Now we delve into one of the most exciting and profound frontiers of artificial intelligence, cognitive psychology-based AI. We are exploring how insights from human cognition, how we perceive, learn, remember, and reason can fundamentally reshape the way we design and build intelligent systems. The central question driving cognitive AI is, why should we base machines on human thinking? The answer lies in addressing the limitations of current AI. While today's deep learning excels at pattern matching, it often struggles with why something is true. Human cognition is the ultimate proof of concept for general intelligence, refined over billions of years. By studying its mechanisms, we aim to overcome issues like the black box problem, making AI's decisions transparent, its insatiable hunger for vast amounts of data, and its tendency to be narrowly specialized rather than broadly intelligent. Our journey begins with the hybrid architecture, which is the foundational design for a thinking machine. We are integrating the powerful paradigms. The subsymbolic layer is our machine's intuition. It's built using advanced deep neural networks that process raw sensory data, like the pixels in an image or the phonemes in speech. This layer provides a rapid, almost subconscious understanding. Above it, the symbolic layer is where explicit thought happens. Here, we use knowledge graphs and logic engines to manipulate abstract concepts and perform rigorous reasoning. The crucial element connecting these two is the neurosymbolic transducer. These are specialized components that translate the intuitive patterns of the subsymbolic layer into the structured symbols that the reasoning layer can use, and vice versa, allowing for seamless communication between the feel and the think aspects of the machine. First, our thinking machine needs to perceive the world, and it needs to do so across multiple senses. Our multimodal perception engine is its eyes and ears. It uses advanced models like vision transformers to understand not just objects, but their relationships within a scene. For language and speech, transformer encoders process and comprehend meaning. Critically, these different sensory streams are integrated through multimodal fusion using cross-attention mechanisms, allowing the system to form a more complete and contextual understanding of events. For example, seeing a dog while hearing the word dog. The output of this module isn't just raw data. It's a structured, symbolic representation, ready for logical processing, like a clear descriptive sentence for the brain. Next, we move to memory, essential for learning and reasoning. Our machine features a dynamic dual memory system. Working memory acts as the machine's attentional workspace, a temporary, limited-capacity buffer where active thought happens, drawing on principles from global workspace theory. It's like our own mental scratchpad, holding only what's immediately relevant. This limited capacity is crucial, forcing the system to focus. For long-term storage, we have an integrated knowledge base. This is a hybrid system. A knowledge graph stores explicit facts and logical relationships, constantly growing and evolving. Complementing this is a vector database, holding conceptual embeddings for intuitive retrieval and analogical reasoning. The process of knowledge consolidation ensures that new insights and learning are permanently integrated into this comprehensive memory system. The heart of our thinking machine is the collaborative reasoning and learning engine. This module orchestrates problem-solving and inference. It houses a suite of specialized reasoners, a rule-based reasoner for logical, step-by-step deductions, a probabilistic modeler for handling uncertainty, similar to how we make educated guesses, and an analogical reasoner, which is key to creativity, allowing the machine to transfer solutions from familiar problems to new, similar ones. The overarching learning mechanism here is meta-reinforcement learning. Instead of just learning what to do, The system learns how to think. It optimizes its cognitive actions, like when to query memory, when to try an analogy, or when to ask for more information, driving its efficiency and intelligence. Just like humans, a thinking machine cannot process everything at once. Our dynamic attention mechanism acts as the system's spotlight, intelligently focusing its computational resources. Leveraging advanced transformer-style cross-attention, it dynamically weighs the importance of different pieces of information, be it from sensory input, working memory, or long-term memory. This prioritization is inherently goal-driven, meaning the system focuses on what's most relevant to its current task or query. This crucial module prevents information overload, allowing the reasoning engine to operate efficiently and effectively, cutting through noise to find what truly matters. A machine that thinks needs a reason to think. The intentional system provides this purpose and drive. It defines a machine's goal hierarchy, encompassing both intrinsic goals like acquire new knowledge and explore, and extrinsic goals such as fulfilling user requests. A dynamic utility function constantly reevaluates and prioritizes these goals, allowing the machine to adapt to changing circumstances. Furthermore, we program a curiosity drive, providing intrinsic rewards for encountering novelty and exploring the unknown. This system is crucial for enabling autonomous behavior, proactive learning, and ultimately, making the machine's actions more understandable and aligned with human expectations. The true power of this architecture emerges when all these modules operate in concert through the cognitive cycle. This is a continuous feedback loop that mirrors how we process information. It starts with perceiving the environment. Then, the attention mechanism focuses on what's relevant. The system then retrieves necessary information from memory and updates it with new insights. This leads to reasoning and learning, where problems are solved and new skills acquired. Based on this, the machine acts upon the environment. This entire cycle then repeats, allowing for continuous refinement of understanding and behavior. This unified loop is what makes a machine not just process, but truly think. The development of cognitive psychology-based AI represents a profound paradigm shift. The future of intelligence, both artificial and natural, lies in convergence, the seamless integration of intuitive neural processing with rigorous symbolic reasoning. We are not merely aiming to mimic human intelligence, but to draw inspiration from it to design systems that genuinely understand and learn. The creation of a truly thinking machine is an immense challenge, but by bridging the insights of cognitive psychology with advanced AI engineering, we are taking major strides towards building systems that don't just compute, but truly comprehend, opening a new era for intelligence itself. I am now happy to take any questions in comments. I will further share the more insights and details about how to build thinking machines and underlying principles in my coming video series. Please subscribe my channel and like the video so that I can bring interesting insights and updates on thinking machines.